We're looking at just one thing in this video, an introduction to magnetic force. And the trickiest thing about magnetic force, what we'll focus on here, is just finding the correct direction for magnetic force. The magnitude of magnetic force is quite a bit more straightforward. As you saw in the reading, we've got this strange thing called a right-hand rule for the direction of a magnetic force. And I've written out the 3 steps here. You always point your thumb in the direction of the moving charges that are going to be feeling the force, and then your index finger will point in the direction of the magnetic field that's supplying that force to the moving thing. And then the other 3 fingers will represent the direction of the force. It makes more sense to talk about this in a specific example than in general and abstract terms. So let's look at this. So imagine a positively charged particle, and the velocity is this way, in the plane of the blackboard and straight up. And then there's a magnetic field pointing in the plane of the blackboard and pointing straight to the right. So what do these rules tell us? That thumb in direction of the velocity of the charge that's going to be feeling a force. So thumb this way, index finger in direction of the magnetic field, and then you take your other 3 fingers and rotate them so that they're perpendicular to the palm of your hand. Perpendicular to your index finger and perpendicular to your thumb. Like your thumb and index finger define a plane, be the same plane as the palm of your hand, and your other 3 fingers are perpendicular to that plane. And once you do that, these tell you the direction of magnetic force. So in this case, it's thumb in direction of velocity, index finger in direction of magnetic field, and then when I turn rotate the 3 fingers clockwise, they're pointing this way, into the blackboard, perpendicular to the blackboard and into the blackboard. So that is the force, the magnetic force on this positively charged particle. If it were a negative particle, the force would be in the opposite direction. That's just what it means to be negative. So the force in this case points this way. There's our usual symbol for perpendicular to the blackboard and into the blackboard. Look at one more example here. Now, a negatively charged particle, the velocity is this way, so I point my thumb straight down. The magnetic field is right to left, so I point my finger to the left, and then I rotate my fingers so that they are perpendicular to the plane in which index finger and thumb sit. And when they're perpendicular, they'll be pointing this way, again, into the blackboard. So that's the direction of the force if we had a positive charge. But we got a negative charge in this case, so the force points the opposite way. It's a strange set of rules, and you just have to get used to the strangeness. I said at the beginning of the previous magnetism video, magnetism is strange and complicated, and this is just one of the strange aspects of it. Let's look at a couple other examples where again, a charged particle is moving, so it's feeling a magnetic field. And in this case, the magnetic field is caused by some current. here's current flowing this way, and we've got a charged particle up here moving in the same plane as the current, the plane of the blackboard, and the velocity of that particle is pointing straight down. And this time we'll say we have a positive charge. So to do the right-hand rule in order to find the force, one thing we need to know is the direction of the field. The field is caused by this current, so we need to think again about what magnetic current caused by a straight current is like. And the key word is circles. The magnetic field lines for a field caused by current in a long straight wire is circles, concentric circles centered on the wire and in planes perpendicular to the wire. So if here's the current, then circles like this would be the magnetic field lines. And for the right-hand rule to tell us whether the magnetic field lines circulate this way or the other way, use the right-hand rule, the other right-hand rule, not the force right-hand rule, but the right-hand rule that connects direction of a current to the magnetic field. For that rule, remember, point your thumb in direction of the current, this way, and then let your fingers rotate, and that will be the sense of the flow of the circular field lines. So, for example, here, when my fingers are above my thumb, remember my thumb represents the current, that means that it points above the current, above my thumb. My fingers are pointing that way into the blackboard. And so that means, and then likewise, below, points below, the thumb is above my fingers. So these fingers represent the field lines below the current represented by the thumb. The curved fingers represent the circular field lines, and below the current they'd flow this way, out at you, at points below. Remember that since field lines make a concentric circle, a field line would actually be half, the circular field line, half of that circle would be here in front of the blackboard, we imagine the other half of the circle behind the blackboard. So the flow of that circle would, on this side of the blackboard, would be like that. And then behind the blackboard, like that. Well, now we have the direction of the magnetic field, so we can figure out the force on this charged particle. Again, thumb in direction of the velocity, index finger in direction of the field. Up here, at all the points above the current, field is pointing into the blackboard, so I point my thumb this way in direction of the velocity, and then my index finger is pointing this way, straight into the board. And then my other three fingers must be perpendicular to the palm of my hand, or in other words, perpendicular to both the index finger and thumb. So now they're pointing that way. That is the direction of the magnetic force on this particle. The particle will will no longer be heading straight at the wire. It'll be deflected to the right. And then one more example like this. Let's imagine current going the other way, and then a charged particle again up here on this side with the same velocity, but now it's a negatively charged particle. So we start the same way. First we have to figure out what the direction of the field is when this particle is moving through that field. And remember, it's circles circling around this line that represents the wire and the current. And again, point your thumb in direction of the current. That means at points up here, points that are above the current, which is represented by my thumb, my fingers represent the flow of the field lines, and above my thumb, in other words, above the current, my fingers are pointing out, so the field points out, straight at you. And then, of course, the field would point the opposite direction on the bottom, below the wire, but that doesn't matter here because this particle's feeling this field, not the field down here. So now use the right-hand rule. Thumb in direction of the velocity, index finger in direction of the field, which is pointing this way, straight at you. So thumb in direction of the velocity, index finger straight at you. Make the other three fingers perpendicular, and so now they're pointing that way. So that is the direction of the force on a positive charge. You have to remember that if it's negative, you have to flip the direction of the force. So this would have been the direction of the force if this were a positive charge, but it's a negative charge, so it goes the other way. Turns out, in this particular case, the force points the same way as this force. One last example. Any charge that is moving can feel a magnetic force. How about lots of charges all moving in the same direction? In other words, current. What would the magnetic force on a current look like? And let's look at a situation where a current feels a magnetic force that's coming from another current. So let's say there are two parallel currents, call them 1 and 2. And first, let's think about the force from 2 on 1. In other words, we're thinking about the magnetic field created by current 2. That's going to be the field that this one feels. And so the field from current 2 is going to be the field that produces the force on current 1. And so, of course, like in the previous two examples, we have to start by figuring out what the direction of the field is, the field that's acting on the moving charges that we're thinking about. So remember circles, and in this case, the right-hand rule for direction of a magnetic field starts by pointing our finger in direction of the current flow, and then our fingers will curl in the sense in which the field lines are flowing, so that at these points here, above and to the left of my thumb, in other words, above and to the left of the current, my fingers are pointing out, meaning the magnetic field all around here, in other words, the magnetic field that's felt by current 1, is a field that's pointing out at us. That's the field caused by current 2, so I call it B2. And now let's think about the force on that current. We have lots of charged particles, and since we're imagining this, as always, to be the conventional current, we think of this current as the flow of positive charge, and they're all moving this way. So the velocity of all those charges is this way. So we point our thumb that way in the direction of the velocity of all these charges. And then index finger in direction of the field, which is out, straight at you away from the blackboard. So there's thumb pointing that way, index finger pointing that way. And to do that correctly, I've got my hand is now sort of at a 45-degree angle, and then rotate my other fingers until they're perpendicular to the palm of my hand, perpendicular to the plane in which index finger and thumb are, and that this way, from pointing this way, is the direction of the magnetic field, magnetic force, that way. That's the force from current 2 on current 1. And it's actually an attracting force. The magnetic force from current 2 is attracting 1 towards current 2. Current 1 is being pulled this way by the magnetic force that comes from current 2. So that's the force from 2 on 1. Now if we're looking at the force from 1 on 2, that force is, of course, a third law partner force to this. So being a third law partner, being the other half of a third law pair, we know it's got to be in the opposite direction, this way. But let's just go through all the right-hand rules to verify that. This is going to feel a force because it feels the magnetic, this is going to feel a force from current 1 because it's going to feel a magnetic field that comes from current 1. So down here, where current 2 is, what's the magnetic field from current 1 like? Thumb in direction of current 1, and then our fingers curl in the same sense as the flow of the circular field lines. So at points when my fingers are below my thumb, in other words, it points below I1, in other words, where I2 is, the field is pointing into the blackboard, this way. That's the field from current 1. Now we use the force right-hand rule. Positively charged particles are moving this way. That's what current in this direction means. So the velocity of those charged particles is this way. So I point my thumb that way. And then the field is pointing this way into the blackboard. So I point my finger, index finger, that way into the blackboard. And again, to really have my thumb pointing in the direction of the velocity, I've got to have my hand rotated at kind of a 45-degree angle again, so that now when I rotate my fingers so that they're perpendicular to thumb and index finger, they're now pointing up and to the right at kind of a 45-degree angle. So up and to the right is the direction of the force on this one. the force from 1 on 2. Current 2 is pulled towards current 1. Right? The force from 1 on 2 is in the opposite direction from the force from 2 on 1, which is exactly what we should expect because they are a third law pair. And of course, third law pair means they are the same type of force. Right? This is a magnetic force, and it's attracting the current to another current. And this is also a magnetic force attracting one current towards another. Same type of force. Okay, but it sounds, it's all kind of strange and hard to get used to, but you will never get used to it unless you do some practicing and try it out. The one thing that you should keep in mind before you try it out is you have to be willing to really move your hand around. So thumb really is in direction of the velocity, not just close to that direction, and index finger really is in the direction of field, not just close to that direction. And curl your fingers around until they are fully perpendicular to index finger and thumb. And to get the correct orientation, and you might have to move around. You might have to rotate yourself. So that you can get the correct orientations without twisting your arm off. And generally, if I see people not really moving their hands or moving them just a tiny bit, that is absolutely a dead giveaway that they're not doing it right. The most important thing in order to get this strange stuff right is to be willing to really move. Okay, so we'll try that in class.